Welcome guys, this is Mr. Ndabezita once again. I'm going to keep this recording up here because Camtasia has some tendency of not doing the things that I want. So I remember previously we discussed the parabola and the function of the values that has to do with this. So in our tutorial you can just go and check what we have said. Right, here is where we will begin at the vertical line test for a function. Right, we read not every curve in the coordinate plane can be a graph of a function. This is true, and we will see as we continue that not every coordinate plane can be the graph of a function. So you can have the points on the Cartesian plane, and when you draw up these points trying to have a graph, we are therefore saying that not every curve that you will find on that Cartesian plane can or will represent a function. And we say a function f can have only one value of y. Remember, this is y, for each value of x in its domain. So this is exactly what we said. We said a function is a relationship, or it is a relation where one value of x is mapped to exactly one value of y, and therefore you are a function. I believe we dealt with that so much in the previous tutorials. So no vertical line can intersect the graph of a function more than once. So when you run the vertical line test, and it only cuts the value for every value of x, you have only one value of y, therefore the function passes what we call a vertical line test. So we are saying no vertical line test can intersect the graph of a function more than once. So when we run the vertical line test, we cannot have a vertical line test that can do what now? That can intersect the graph of a function more than once. So we are simply saying that when you run the vertical line test, we cannot have the values of the domain that are mapped to more than one value of y. If there is such a case, therefore it is not a function because it fails the vertical line test. Right, if a is in the domain of a function f, then the vertical line x equals a will intersect the graph of f at a single point. So you have the value of a, you have a machine f, and you are substituting the value of a in order to find the value of y. So for every value of x, there's only one value of f at a. A circle cannot be a graph of a function since some vertical lines intersect the circle twice. We will investigate and see that. The circle graphed in figure 1.7a, however, does contain the graphs of functions of x, such as the upper semicircle defined by the function y equals, or f at x equals the square root of 1 minus x squared. We can draw this graph and you will find a circle. Remember, it's plus or minus, and the lower semicircle defined by that. So you have the upper circle where the values of y are positive, and you have the lower semicircle where the values of y are negative. And we can have a graphical representation of that. So this is what we have. The graph of x squared plus y squared equals 1. The radius it's 1. This is a unit circle, and we can see that it fails the vertical line test. Why? Because for one value of x, we have two different values of y. So x is mapped to more than one value of y, therefore it fails the vertical line test. So we can restrict the domains of f such that we can have a function. So remember, here we can solve for y. We can say y squared equals 1 minus x squared, and then y equals the square root of 1 minus x squared. Very good. And remember, when you introduce the square root, you have two values, positive and negative. So here we have a positive, that is the upper semicircle that you see there, where these are the values of the x-intercepts. Whenever you say 1 minus x squared should be greater or equals to 0, you'll find x equals 1 and x equals minus 1, and the y-intercept will be a value there. And then you can draw this semicircle. And then for the other part, minus the square root of 1 minus x squared, it's this lower part there. So these ones are functions. Why? Because for every value of x, you can only get one value of y. So these ones passes what we call the vertical line test. So there is a one-to-one relationship that is happening between the values of x and the values of y. So the circle is not the graph of a function, referring to a full circle here, because it fails the vertical line test. We can see that. And then in B, the upper semicircle is the graph of a function. We know and understand why. And the lower semicircle is also the graph of a function. So basically, we have restricted the graph of a circle, a unit circle, to only accommodate the positive side, the upper semicircle, and the lower semicircle, in order to have a function. Alright, that is fine. And then we have a piecewise defined function. And before we look at this piecewise defined function, which we have these two parallel lines, which we call the modulus sign. So we have the graph of the modulus here. The absolute value function as the domain, negative infinities to positive infinity, and we can see that it's heading towards negative infinity and heading towards positive infinity in terms of the domain of this function. So we have this modulus. Now let me just show you something so that we may understand how this graph was graphed. Let me just go here and let me just bring it very closer here. Now remember, we can choose any integer values that we want. So let's draw this graph from -3, for example. So you'll have the modulus, which are those two parallel lines. We should have them somewhere here. I think this calculator has that capability. Let me just look very quickly if I can see that. Okay, let me see. Unfortunately, it looks like I don't have the modulus sign around here. I just don't have the modulus sign, or maybe it's me who doesn't see it. I don't know, but I can explain what is happening here. So the modulus sign, for every negative value you insert inside of a function, it will always give you a positive value. So when you say the modulus of a negative number, it will give you a positive. The modulus of a positive will also give you a positive. So we can come here and substitute x for -3 in here. You will say the modulus of -3 and it will give you 3. So when x is 3, y is 3. When x is -2, y is 2. X is -1, y is 1. And then you will have when x is 0, y is 0. So you have this piece first, and then secondly the same thing will transpire. So this is how it looks like. It is called the absolute value function, or the modulus graph, and it can be transformed. We can take it up or down, left or right. Many things can transpire, but I want you to look at something here. The graph of y equals -x. And what is this? This is a straight line. You can see that we are having two straight lines, but this side the gradient is negative and the value of c is 0. We don't have any y-intercept there. So it intercepts at 0 and 0. So we have this function for y equals minus x. We have this piece, and we have another piece of y equals x where the gradient is positive. Very important, and it has this domain, and the range you can see it's from 0, and 0 is included because the graph is defined at 0 going that way upwards, so to positive infinity. All right, be that as it may, let's look at some piecewise defined function. This is very important that we understand this. Sometimes a function is described in pieces by using different formulas on different parts of its domain. So we can take different parts of the graph and try to explain the different domains. For example, we can take this part, which is a full graph. We can take just this part and just define this piece, and we can also take that part and just define that part. So we have the modulus, which is a function, and the modulus of x equals x when x is greater or equals to 0. So meaning for positive values of x including 0. And which ones are those? Here they are. So we are defining this piece. And the modulus of x for x equals minus x when x is less than 0. And there we are defining this one, because this is minus x for x is negative. And where are the values of x that are negative? Those ones. So we have taken a full function y equals the modulus of x, and we are defining it in pieces, the first piece and the second piece, and this is how we write it. Very, very important that we understand that, right? So one example is the absolute function was graph in figure 1.8. The right hand side of the equation means that the function equals x for x is greater or equals to 0, which is this part, and equals minus x if x is less than 0, and there it is. Piecewise defined function often arise when real world data are modeled. Here are some other examples, and we are going to look at the real world application of these piecewise defined functions, maybe in restaurant or maybe in petrol or whatever. It applies in many real world applications. Now this is another piecewise defined function that we have in here. Notice that we can define this piece, and we can define only that piece, and we can define also that piece. So there are three pieces that we can define in this graph of y equals f at x. So first of all, we are here y equals minus x for values that are less than 0. There they are, nothing new with this, same as that. So here we are. And then secondly, we can define this graph here from 0 until to this point where x is 1 and y is 1. And we can say, because remember, this is a parabola, this was a parabola, but we have taken only the other piece. So we are saying x squared for x is between, remember we are speaking about x values here. We are defining this function from 0 up until 1. So from 0 here up until 1, we are having this second formula x squared. And then secondly or lastly, y equals 1. So y equals 1 if x is greater than 1. So x is greater than 1, we are accepting any values here. So for every value there is, the value of y does not change, it will remain at 1. Irrespective of what value of x you use here, even if it can be 100, the value of y remains constant. Y is equals to 1 for what now? For the values of x that are greater than 1. That are greater than 1. Very important that we note that, please. Okay, figure 1.9 to the graph. The function y equals f at x is shown here. We apply different formulas to different parts of its domain. Okay, that is fine. And we are saying here are some other examples. Okay, we have this. The function is defined on the entire real line, but has values given by different formulas. This is true that the function is defined on the entire real line, because look here, it is approaching negative infinity, and look there, it is approaching positive infinity. Therefore, we are saying the graph is defined on the entire real line. We are speaking of the real number system here. But it has values given by different formulas depending on the position of x. Remember, we are speaking about functions here. The values of f are given by y equals this. We have already defined that. The function, however, is just one function whose domain is the entire set of real numbers. Very important. The function, however, is just one function. This is just one function. All right, and then we can go on and look at the greatest integer function. The function was value at any number x. A function was value at any number of x, any number that you can think of in the real number system. Is the greatest integer less than or equals to x? So it has to be less than, or it has to be equals to x. The function was value at any number x is the greatest integer, not the largest or the biggest value. The greatest integer less than or equals to x. And there it is there. We have x, values that are equal to x or bigger than x. Values that are equal to x or bigger than x. Values that are equal to x or bigger than x. Values that are equals to x or bigger than x. And this is what we call the greatest integer function. And as you can see that it is defined, or it is drawn on the line y is equals to x, and this is a straight line where the gradient of the function is positive or equals to 1. Okay, that is fine. Let's continue in this. They say to us here, the function was value at any number x is the greatest integer less than or equals to x is called the greatest integer function, or the integer floor function. It is denoted by these brackets. Figure 1.10 shows the graph. Observe that. It is important that we observe this. What is it that we need to observe? If you substitute the value of x as 2.4, for example, let's look at 2.4 might be a value somewhere there. You get the value of 2. So it is very important that we note something here. Right, 2.4 is the greatest value of the input value 2. So when you input a value of 2, you get a greatest integer value of 2. So you input 2, for example, and then you get the greatest value. You input 2.4 and you get a value of 2. So what are we seeing here? I want us to note something. When we have a 0, when x is 0 here, y is 0. But when x is 0 here, there it is moving to 1, but we have an open circle at 1. When it is at 1, it moves towards 2. When it is at 2, it moves towards 3. When it is at 3, it moves towards 4. So it moves towards the greatest integer function of the value of x. This is exactly what we are seeing here. So we have 2.4 and we get 2. We have 1.9 and we get 1. So this value of 2.4, and then we are getting 2, 1.9, and then we are getting 1. To me, it seems like if you are inputting a value of 2.4 as x, and then you get 2, what it simply means is that when you are at 2, the greatest integer value will be 2.4, and when you are at 1, the greatest integer value will be 1.9, and when you are at 0, this is 0, and when you are at negative 1.2, it will take you to the value of minus 2. So when in essence, when you are at minus 2, you get a value of negative 1.2. So negative 1.2 is the greatest integer value of minus 2. And when you are at 2, it gives you a value of 2. And when you are at 0, it will give you 0.2. And then when you are at negative 1, negative 0.3. And when you are at negative 2, it will give you negative 2. So this is the greatest integer function. And one thing that we need to note in here, when you have this line y equals x, in this case, the greatest integer function, you can see that it lies to the right of y equals x, this straight line, and then we can also move this to the other side so that it moves in that way, so that it goes in that way. So we can represent it in many ways. We can also have y equals minus x, and it can be on this side or it can be on that side. Or we can just translate this to this part, maybe somewhere here, and we can have it on the right of y equals x or on the left of y is equals to x. So the function whose value at any number x is the smallest integer greater than or equals to x is called the least integer function. So this one is the greatest integer function. Why? The function whose value at any number x is the greatest integer less than or equals to x is called the greatest integer function. So the number x, any number x, is the greatest integer less than or equals to x. So you can have an x value which is 2.4, and you get a value that is less or equals to 2.4. So this is what we call the greatest integer function. You can have an x value that is greater or equals to x. So when you have 2.4 and you get 2, because this 2.4 gives you a value that is less or equals to 2.4, therefore this is the greatest integer function. As you can see here, for 1.9 we get 1. So 1 is less or equals to 1.9. Very important, and this is the greatest integer function, and it lies to the right of this straight line y is equals to x. So when you substitute a value of x that is bigger than the value that you get of y, therefore this value of y is less or equals to the input value of x, therefore you get the greatest integer function. Right, so 2 is less or equals to 2, nothing is new here. And 0.2, we know that 0 is less or equals to 0.2. And also we know that negative 1 is less or equals to negative 0.3, and we also know that negative 2 is less or equals to negative 2. So in most cases, I want us to draw attention to where we have different values. When you input a value of x and you find a value of y that is less than the value of x, less or equals to the value of x, and therefore it represents the greatest integer function. Let's just draw that conclusion. And then in example 6, the function whose value at any number x is the smallest integer greater than or equals to x. Now let us listen to this statement. the function whose value at any number x is the smallest integer greater than or equals to x is called the least integer function or the integer ceiling function. It is denoted by that. Okay, that is fine. In figure 1.11, we will go and look at that and see what is happening. Now in this one, I think it is very important that we see something here, something which is worthy of noting. Right, in here, y equals the greatest integer function in terms of x. Right, let us look what is happening here. For value of x, for example, let's say we have x as 1 and we have y equals x, so it lies on that side. And this time, look what it does. If we have 2, it points to a lower value. If we have 3, it points to a lower value. If we have 0, it points to -1, -1, -2, -2 to -3. Let's see a contrast. This was the greatest integer function. For the value of the input that you input, for example, you input a value of 2.4, and we know that you get the value of y, which is 2, and 2 is less or equals to 2.4. So for every input value, if you get a value that is less or equals to the value of x, is the greatest integer function. But here, look what is happening. This one points to a value that is higher, and this one points to a value that is lower. Therefore, this is what we call the least integer function or the integer ceiling. So it points to lower values, it will produce the least integer function or the integer ceiling. When it points to a higher value, it points to the greatest integer function. This is just how I see this greatest and the least integer functions. Alright, be that as it may, there may be different ways of explaining that, but this it makes sense to me when I explain it in that way. So when you have a value that points to a value that is less, therefore you have the least, and when you have a function that points to a higher value, then you have the greatest integer function. And for every input value, you should get a value that is less or equals to the input. Therefore, you have the greatest integer function. Right. So for the least integer function, for every value of the input that you input in here, you will always get a value that is greater or equals to the input. Therefore, you have the least integer function. If the graph of a function climbs or rises as you move from left to right, we say that the function is increasing. Right. What are we saying here? If the graph of a function climbs or rises, it climbs or it rises, it is moving upwards or it is climbing upwards. If the graph of a function climbs or rises as you move from left to right, so if we are moving from left to right and the graph is climbing or it is rising, for example in here, just take a look at just this piece, we will say the graph is rising or it is climbing as I am moving from left to right. As the values of x are increasing here, look at the function. The graph is climbing or the graph is moving upwards. Therefore, it is increasing. This is very, very important that we understand that. For the x values that we have, if we are moving from the left towards the right and we are increasing the values of the domain, and by so doing our graph, our function is climbing or our graph is moving upwards, therefore we are saying it is increasing. If the graph of a function climbs or rises as you move from left to right, we say that the function is increasing. If the graph descends or falls as you move from left to right, then the function is decreasing. Now we can see this in here. Right. So as we descend, as the values of x are getting small, as the values of x here they are getting smaller and smaller, our function also is descending, therefore it is decreasing. So when you are moving from the right to the left, as they are saying, if the graph descends or falls as you move from left to right, so as we are moving from the left to the right, the graph is decreasing. We are moving from left to the right, the function is decreasing. So as the values of x are decreasing, as you can see here, so are the values of y, and therefore the function is decreasing. As the values of x are increasing, so are the values of y, and the graph is increasing. So increasing and decreasing on the Cartesian plane deals with the values of x and y. So if the value of x increases and an increase in the values of x results in an increase in the values of y, therefore the function is increasing on that interval. And when the values of x are decreasing as we are moving from left to the right, so is a correspondence on the values of y will also decrease, therefore the function is decreasing on that interval. Very, very important we understand that. So please look at this in terms of the coordinate system, both the values of x and y, what is happening to them. So as we are moving from left to right, both x and y increases, therefore the function is increasing. And as we are moving from left to the right, as you can see here, is if we move from left to right, the values of x as they are decreasing, so are the values of y, therefore the function is decreasing. And as we are moving from left, if we are moving from left to right on the side here, as the values of x increases, therefore the values of y are also increasing. And in this one, I want to stress a point here. As we are moving from the left, very important, if we are moving from the right to the left, we have been moving from the right to the left. Let me put it in that way, because it is a little bit confusing if we say the graph descends or falls as you move from left to the right. So this, we are moving here, and when we go to that side, we are saying we are going to the right, and when we are going to that side, we always say we are going to the left. So let us just simply say, as we are moving from the right to the left, the function is decreasing, and as we are moving from the left to the right, the function is increasing. So as we are moving from the right to the left, the function is decreasing. Let's just be careful of that. And as we are moving from the left to the right, the function is increasing. Please, let's just try to correct that, because it might create some confusion here. How is it possible that left to right increases and also left to right decreases? So we need to swap the things there. As we are moving from the right to the left, the function decreases. From left to right, the function is increasing. All right. Definition: let f be a function defined on an interval I, and let x1 and x2 be any 2 points on this function. Now remember, we are speaking about functions here, and this function that we have, which is a machine, we are having certain values of the domain that we want to input inside of a function, so that we can get the corresponding values of y. And for each value of x, there should be a corresponding value of y. And therefore we are saying for x1, which is the first value we are inputting in a function, and the second value that we are also inputting in a function, can be any 2 points on this machine, on this function. So if you input the value of the second value here in a function, and you find that the value of y is bigger than the value of y when you input the first value of x. So here you are having the first value of y. If you are inputting x1 and the first value of y is smaller than the second value of y when the input was x2, whenever x1, if the value of x1 is less than the value of x2, then f is said to be increasing on that interval. Let us check with this practical example here. We have x2 here, and if I substitute this on this function, when x is 2, I will get y as 2. There it is. And I input the value of x as 1. When x is 1, y is 1. So look what is happening here. F at 2 is greater than f at 1. And the value of x2 is bigger than the value of x1. We are here. Then f is said to be increasing on that interval. And it is true. You can see there will be an increase. So nothing is new in this. If f at x2 is less than f at x1, which is y here, if you input the value of x2, you get the value of y in that machine, and you find that value to be less than the first value, then it is decreasing. Let us take a practical example. Let's say this is x2. I input this value when x is 3, y is 3. Okay, and then I'm here, x2. Let's say this is x1. There it is, and say this is x2. If the value of x1, which is this one, let's say this one, if the value of x1 is less than the value of x2, therefore the function is said to be increasing there. But I don't think this is a great example that I have made. Now, a decrease. Let's look at the decrease here. When x is minus 1, look what is happening here. When x is minus 1, y is minus 1. When x is minus 2, y is minus 2. And I can see that x1 is bigger than x2. Very important. So if f at x2 is less than f at x1, whenever x1 is less than x2, so x1 needs to be less than x2. Okay, so x1 needs to be less than x2. So let's say this is x1, because x1 needs to be bigger than x2. So let's say this is x1, because minus 1 is bigger than minus 2. Now let us check. With x1, when the value of, when I substitute there, I will get y as minus 1. And when I substitute a smaller value there, I will get x2 as minus 2. Therefore, if at f at x2, which is this one, is less than f at x1, and it is true that minus 1 is bigger than minus 2, and if that is true, then f is said to be decreasing, and it is true that we can see that it is decreasing there. So the statement holds true when we look in here. It is important to realize that the definitions of increasing and decreasing functions must be satisfied for every pair of points x1 and x2 in that interval, with x1 being less than x2. We have saw that. Because we use the inequality less to compare the two function values instead of less or equal, it is sometimes said that f is strictly increasing or decreasing on that interval. The interval I may be finite or finite, also called bounded. So when it is bounded, we simply mean that we know the beginning and the end. So we have a closed interval in that way. Or infinite and unbounded. So we have maybe negative infinities to positive infinity. It is unbounded. And by the definition, never consists of a single point. By definition, it can never and ever consist of a single point, because how will we know if we only use a single point whether the function is increasing or decreasing? It has to be compared with at least a minimum of 2 points. then we can say whether it is increasing or it is decreasing on that interval. All right, that's fine. And then they say to us the function in figure 1.9. okay, we passed that one, that is fine. Now let us look at even functions and odd functions, symmetry in other words. The graphs of even and odd functions have characteristic symmetry properties. Definition: a function y equals f at x, which is the value of y. So to find y, you plug x on a function or on a machine and it will tell you what value of y is even function. This function is an even function of x if you substitute a negative value in your machine and you get a positive value. Therefore, that function is even. If you have a machine, for example, y equals the square root of x, and you input the value of x inside of a machine and you get a positive y value, therefore it is even. The function is even. And if you input a negative value of x, the interval inside of a machine, and you get a negative y value, therefore the function is said to be odd. For every x in the function's domain, not only for a few values of x, for every x that you have defined in that domain. Very, very important that we understand that. The names even and odd comes from the powers of x, the exponents of x. Let me put it that way. If y is an even power of x, as in the function y equals x squared or y equals x4, it is an even function of x, because negative x squared equals positive x squared and negative x equals positive x to the exponent of 4. So you can have a table of values x minus 3 minus 2 minus 1, and if you plug that in here, for every negative value of x you input there, you will always get a positive value of y. Therefore it is even. Even here, why? Because these are even numbers. So for every exponent of x, or for every power of x that is even, the values of x that you plug in here will always give a corresponding positive y value. Therefore we say that it is a function, right? If y is an odd power of x, as in y equals to x, because for example, if I have a table of values and I try to input the value of x as minus 1 here, I'll get y as minus 1. So because the y value is negative for every negative x value, therefore the function is said to be odd. And we can have that for x exponent 1, 3, 5, 7, and so on. It is an odd function of x because minus x exponent 1 equals to that. Okay, that is fine. Let us continue in this. The graph of an even function is symmetric about the line about the y-axis. There is the y-axis, and the graph of an even function, remember this is even, so the graph of an even function is symmetric about the y-axis. For every input value of x in your machine, you will always get a positive y value. A point x and y lies on the graph if and only if the point minus x, when you input a negative value of x, you get a corresponding positive y value. So this is important that we understand this. So for every even function, it will be symmetric about the line or about the y-axis. So you have x and y, there they are. And even if you input a negative value of x, you'll always have a positive y value. So this is a symmetry about the y-axis. So guys, I think I'm going to pause it in here, and then when we meet in the next tutorial, I think we will just go and look at let me see, we will just go and look at rational functions. So thank you very much guys for your time, and I will see you in the next tutorial. Okay guys, here we are. Let's just continue in this. So we explained the symmetry about y exists, and I explained everything what is happening in here. And then the graph of an odd function is symmetric about the origin. Very, very important that we note that. We know this is an odd function because we have the exponent of 3 there. So we are therefore saying the graph of an odd function is symmetric about the origin. Why? Because we know that when you input a negative value in your machine, you will get a negative corresponding y value. Very important. A point x and y lies on the graph if and only if the point minus x and minus y lies on the graph. Let us try to understand that. A point, when you have two positive x values, two positive x value and a y value, so you have a coordinate where both an x and y are positive and they lie on a graph. Let's make an example here. When x is positive, y is positive. Lies on the graph if and only if the point minus x and minus y lies on the graph. So this is a symmetry about the origin. So we are saying the function is an odd function if you have a point, for example in here, where both x and y are positive, and you get a corresponding point x and y that are both negative. A point x and y lies on the graph if and only if that lies on the graph. Equivalently, a graph is symmetric about the origin if a rotation of 180 degrees about the origin leaves the graph unchanged. Very, very important. So let me just make a pause guys, and I will come back. Right, so here we are, we are saying equivalently a graph is symmetric about the origin if a rotation of 180 degree about the origin leaves the graph unchanged. And we know that when we rotate this point 180 degrees, it will find itself, remember we will rotate it 90, it is in here, x is negative, y is positive, and you rotate it another 90, it is in there where both x and y are negative. So this is how this rotation works. About the origin leaves the graph unchanged. Yes, it leaves the graph unchanged very much, because you still have, remember, y equals x3, here it is, and we have left the graph unchanged. So we are therefore saying a point lies on the graph if and only if the point minus x and minus y, that one, lies on the graph. Equivalently, a graph is symmetric about the origin if a rotation of 180 about the origin leaves the graph unchanged. It has to leave the graph unchanged. Notice that the definitions imply that both x and minus x must be in the domain of f. Very, very important that the value of x and minus x, let me just show you this. Let me just take this one up there. The value of x and the value of minus x, there they are. Notice that the definition implies that both x and minus x must be in the domain of f. Very, very important that the value of x and the value of minus x must be in the domain of this function. Very, very important when you perform this rotation about origin. Here are several functions illustrating the definition. So we have the first one, f at x equals x squared. It's an even function, we understand that, and then even this one will still be like that. Symmetry about the y-axis, and we saw that even functions are symmetric about the y-axis. We saw that. And look what is happening in here. Just to brief you, only the value of x changes the sign, because the value of y is positive in the second quadrant. Only the value of x is negative. So okay, that is fine. We can look at many of that. Nothing is new. Common functions, we have spoken about those ones. And then we can continue in here. We spoke about odd functions, even, odd, even, and odd. As long as it doesn't change the shape of the function, it can be rotated about the origin through 180 degrees. We saw all that, so I'm not going to explain that any further, right? And then what is it that we can say? A rational function. I think it is very important. Or let me just go and look at the definitions of a polynomial, or try to even explain some of these functions here. Right, common functions. A variety of important types of functions are frequently encountered in calculus. We identify and briefly describe them in here. Linear function, a straight line function. In other words, a function of the form f at x equals mx plus b for constants m and b, because that's exactly what they are. M is a constant, it is a gradient. B, it's also the y-intercept, the value of c, so they are constants because they are numbers. It's called a linear function. Okay, that is fine. The function f at x equals x, where m equals 1 and b equals to 0, is called the identity function. Constant functions result when the slope is equals to 0. A linear function with positive slope whose graph passes through the origin is called a proportionality relationship. And we have them in there. Definition: two variables x and y are proportional to one another if one is always a constant multiple of another. So this is a proportionality that we are looking at, and we are saying, let me just come here, two variables x and y are proportional to one another if one is always a constant multiple of the other. For example, if y equals k at x for some non-zero constant k, if the variable y is proportional to the reciprocal of 1 over x, then sometimes it is said that y is inversely proportional to x, because 1 divided by x is the multiplicative inverse of x. And then we have power functions and so on. Here they are. I'm not going to dwell very deeper into all this, quadratics and so on. Let's go to rational functions. A rational function is a quotient or a ratio f at x equals p at x divided by q at x, where p and q are polynomials. Very important. The domain of a rational function is a set of all real x for which the denominator is not equals to 0. The function that is on the denominator should not be equals to 0. The graphs of several rational functions are shown in here. Okay, this is just a brief summary. And then we have algebraic functions, trigonometric functions. You can have a look at that for yourselves. Now, this is what we are going to deal with. In exercise 1 up until 6, find the domain and the range of each function. So this is what we are going to deal with, and I'm not going to solve entirely all these problems. I'm just going to solve 3 of them because we have 6, and then I will leave you to solve the other 3. So this is exactly what we will be dealing with in this tutorial.